and get the screen slideshow on the current slide. Okay. All right. Now, my mark that I think I was supposed to leave it on was on page 528, just under that conceptual insight box. And that was talking about another infinite series. I'll put this away, I don't know. What's that? Okay, you stop there? Okay, example 6, bottom of the page. Sum of geometric series, that's the last you had? Okay. Yeah, here's the silver. Okay. I don't know why. Oh, well, that could have been a mark from the last class. I mean, the last time I taught this or some previous time I taught it. But I don't have a mark here on this page.
Maybe we did get to
What's that?
Maybe we did get to
Okay.
What are we looking for? Oh, we're supposed to appear.
What's that?
We're supposed to start from there.
From there? Okay. Actually, I had my mark a little bit before that. One other infinite series, which I think tell me if we did this already. Here's an infinite series. I'm pretty sure I know we did it more than just, we've hit this several times. This infinite, well, maybe not. Let's see. Infinite series, summation k equal 1 to infinity of 1. Okay. What would that be? One plus 1 plus 1 plus 1 plus 1. Well, obviously, the series doesn't. The sequence doesn't converge. 1, 1, 1, 1, 1, 1, 1. Okay, it does converge. Okay, but the sequence, the series, the summation of those certainly doesn't. 1 plus 1 plus 1 plus 1. Going to infinity, infinity, 1 million, 1 million, 1 million, 2. 10,583, 10,584, just keeps growing. Certainly that diverges. No problem there. However, it says it's less clear when you have a summation such as this. Summation n, why they changed the indices, I don't know, but they do. It doesn't matter. You can name them anything you want to. From 1 to infinity, starting off with -1, and Marcus is here, so we're just missing Faith. All right. Sorry. Okay. -1 raised to the n plus 1 power, okay, of n over n plus 1. Okay. Give me the first term in that sequence. What does the -1 to the n plus 1 do for you? Okay, the first sequence, the first term would be 1. But what -1 to the n plus 1 does is alternate signs for you. That's all it's doing. It's plus 1, minus 1, plus 1, minus 1, plus 1, minus 1. Okay, and it starts with plus 1. Okay, then what does this next one do? N over n plus 1, that would be for the first term. Yeah. First term would be 1 over 2, and then we'll change signs, minus 2 over 3, change sign, plus 3 over 4, minus 4 over 5, plus 5 over 6, minus 6 over 7, plus dot, 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 dot. Okay, it just keeps on trucking there. Okay. Now, certainly the series, the sequence converges. 1 over 2, this part. That converges to 1. But it's not real clear. I think it would be clear that if you had all plus signs there, that's getting close enough to 1, it's going to sort of act like that, okay? Like 1, okay? It's not, doesn't look like to me that would converge because every term's getting bigger, so you always would be adding a bigger. But with the plus and minus there, it's not as clear because now you're subtracting and adding, subtracting and adding, subtracting and adding. And it's not really clear what's winning. You start with 1/2, then you subtract something larger than 1/2, so that's going to be a negative number, okay? Then you're adding something back that's going to make you positive again, and then subtracting, you know. Now, the question is, okay, the difference between these two is, see, that would be 6, negative 1/6, right? I mean, when you add those two together. And then add to that 3/4, common denominator of 24, that'd be minus 1/6 plus, would that be 18/24? Is that 3/4? No. Yeah, 6/24, 12/24, 18/24, yeah. Yeah. So that would be 4/24, 18. That'd be positive 14/24. And then, I mean, it just gets really awkward and not real clear whether by the smaller number subtract the bigger number from it, you get a small negative number, then you get a bigger positive number, but then, you know, negative. It's not real clear what's that going to do. Is it going to converge, diverge, what? Okay? So, what we're going to do here is introduce a useful test that allows us to conclude that this series does indeed diverge. The idea is that if the terms are not shrinking to 0 in size, then this series will not converge. If the terms aren't shrinking to 0, the series will not converge. And that's the problem you have here. The terms are getting larger, and even though you're alternating signs, you're doing something bigger to it every time. So the idea is this is a 1/2, subtract 2/3, it goes slightly negative. But then you're adding 3/4, and that gets you bigger than you were when you started. And then subtracting 5/4, I don't know what it's doing, but you're doing bigger numbers, so they are getting further apart, but they're a changing sign, but it can't. That's what this is saying. If the terms aren't going to 0, there's no way this is going to converge. And that's what this theorem says. It's your divergence test. Now, in the old, no, I'm sorry. In the old text, which De Silva has, it's called, this is exactly what it's called, the divergence test. In the new text, the new edition, it's the nth term divergence test. It's the same thing, I believe. I haven't compared completely, but I believe it is. It's sort of saying it slightly differently, but it's saying if the nth term, a sub n, does not converge to 0, then the series, the summation n to infinity of a to n, a sub n, diverges. That is absolutely, obviously true when the signs are the same. Gotta be. If that nth term is not converging to 0, there's no way that the series, which is adding something that's not 0 every time, that's going to diverge for sure. Now that's slightly different here. Here it says the nth term divergence test. If the limit as n approaches infinity, see this doesn't even have the limit in there, of a sub n is not equal to 0, which is basically what that is saying, if the nth term does not diverge to 0. So if the limit, just say it differently, then the series, and then this says it exactly the same, diverges. So it's just the way they say this phrase here. In the new text, they put this as a limit, okay? But it's saying the same thing. So, identically the same thing. Now, and this is also in the side note of the newer edition, says also known as the divergence test, so it is the same. In practice, we use it to prove that a given series diverges. It is important to note that it does not say, now this isn't saying it quite the same way, it does not say if that nth term does converge to 0, that guarantees that the series converges. It doesn't say that, okay? It just says that if it doesn't converge, there's no way you can get it to go to 0, to converge, that it definitely will diverge. So this is one of those that the if-then goes one way, but not necessarily the other way, okay? The conditional statement there goes one, but not necessarily both ways. And we'll see an example of that, I think, coming up. No, we don't see it coming up. So let me go and hit it now. I thought they had this. Yeah, let me just do this one. Here's a sequence, a series, I'm sorry, summation n equal 1 to infinity of 1 over n. Now, first, that sequence definitely converges to 0, right? 1, 1/2, 1/3, 1/4, 1/5, 1/6, 1/7. Those are very slowly going to 0. So the nth term, a sub n, does converge. Does that mean that this series converges? No, it doesn't. In fact, and they do nothing more than saying it diverges, and they don't say why. But if you, like I was just doing, think of adding all those things together, even though that they're getting smaller out there, they're not getting smaller fast enough is the deal. They keep adding to each other, and it keeps increasing, okay? Now, it can keep increasing but go to a limit. This one doesn't go to a limit, and they don't say why. We'll get to that a little bit later, okay? Now, here is the next example. It's example 7. Oh, wait, they do. Okay. They prove that statement, and it's well worth reading. It's a pretty simple proof, but go through and look at it. But let's look at example 7. What I think I'll do is clear all the ink off here so we have room to do it. Prove the divergence of this one. S is equal to N, S is equal to, it's a series, the summation of N equal 1 to infinity of N over 4N plus 1. Okay. It says prove the divergence of that one. Okay. Now, what's the easiest thing to prove about divergence? What is the easiest test to make? See if the sequence, does all it take is for the sequence to converge? Is that enough? No. It has to converge to 0. So the easiest thing to do is evaluate that nth term. If it doesn't converge to 0, no way a series will converge. Not just require that it converge, but it has to converge to 0. Does that converge? What was the little trick we used to test a sequence like this? N over 4N plus 1. Yeah, divide numerator and denominator by the maximum power of your index. So that would be dividing by n. Be n over 4n over n plus 1 over n. Do you buy that? You divided the numerator by 0 and the denominator by 0, right? I just did it. A few more terms there. What's that numerator come out being? 1. No matter how big n is, that would be 1. Okay? That denominator, first term there, 4 plus, second, yeah, but n's going to infinity, so that's going to 0. So that'd be 1 over 4. Small number, right? But it's still not 0. So basically, when you get big enough numbers, when you have smaller n's, they're even going to be bigger, but after a while, the closest you can get is adding 1/4 plus 1/4 plus 1/4 plus 1/4. Guess what? That's never going to converge. It just keeps getting bigger. So by proving that the nth term doesn't converge to 0, that shows that the sequence has to diverge. That's all you have to do. Okay? Does that make sense? All right. Let's see if we can do example 8 then. I didn't need as much room as I was afraid I would. Okay? Doubt if I'll need it here, but it might. Determine the convergence or divergence of this one. S, this series, is equal to n equal 1 to infinity, summation of n equal 1 to infinity, minus 1 to the n minus 1. What does that do for you? Alternate signs. That's all that does for you. Of n over n plus 1. Okay? Now, isn't that, yes, that's exactly that one that we had before. It looks a little different. Do you see how it looks different? Before it was n negative 1 to the n minus 1. Now it's before it was negative 1 to the n plus 1. Now it's to the n minus 1. All that's doing is alternating signs, so who cares what your counter starts with? It's going to be plus minus plus minus plus, or minus plus minus plus. Yeah. So this is exactly the same one we had before. And all that we have to show is that this term doesn't converge to 0. We know it converges. What does it converge to? What would you do? What would be your trick? Divide by 1. By n, I'm sorry. and it goes to 1. N over n over n plus 1 over n. And what does this do? Numerator goes to 1, denominator to 1 plus 0. So that's 1, so that's going to 1. 1 plus 1 plus 1 plus 1. We've already seen that divergence. So that's all you have to do. That minus 1 to the n minus 1, the alternating sign, not enough to get it to converge. It's going to diverge. Okay. Now, all right. Now, I think we've hit this one too. If a sub n does not tend to 0, okay? If a sub n does not tend to 0, then the summation of a sub n absolutely diverges. Always. If it tends to, converges to 0.0003, okay? But then you just keep adding terms that are something greater than 0.0003, you're never going to converge, okay? So, that's all it takes, okay? What if a sub n does tend to 0? In this case, the series may converge or may not converge. In other words, the limit, here's how we're going to say what we've been talking about. The limit as n approaches to infinity of a sub n is equal to 0. Now that's talking about the sequence of numbers a sub n. If that goes to 0, that's required before the you can say that the series converges. That's got to happen. It's a necessary condition, but it's not a sufficient condition. Just proving that goes to 0 doesn't tell you it converges. All it tells you, if it doesn't go to 0, you know it diverges. So it's a necessary condition, but not a sufficient condition. Okay? Those are the terms they're dealing with. Okay. Now, they say to prove this one, and it's probably going to take more steps, so let's get the, erase all the ink and we'll come back. This is example 9. Prove the divergence of this one. Whoa, where did that come from? Okay. The summation, n equal 1 to infinity, of 1 over to the square root of n. Okay? Oh, you tell me the first few terms of that. 1 over square root of 1, which is 1, plus square root of 2, plus 1 over the square root of 3, plus 1 over 2, plus dot, dot, dot. Right? Because square root of 4 is 2. So, okay. Now, the square root of n, as n goes to infinity, that's going to 0. That doesn't prove that this converges. It just says, if it didn't go to 0, you knew it diverged. This one does go to 0, but that still doesn't mean that the series converges. Now, they use a technique here for doing this. Let's call this the nth partial sum of that sequence. And let's just say that's just like we did, 1 over the square root of 1. This is dumber, but I'll do it. Plus 1 over the square root of 2, plus 1 over the square root of 3, plus 1 over the square root of 4, plus 1 over the square root of 5, plus dot, 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 and Is Faith here? Perfect attendance today. Way to go, team. Everybody's here. Now, for those who did come in late, since I won't see you probably, well, hate to say this, y'all probably can't go to this anyway, but it's up to you. I don't want to say you can't. Wednesday, which is the next day we meet. And we meet starting at 12 o'clock. And we go until 1:40, right? Okay? This thing starts on the Birmingham East Campus at 1 o'clock. So I know y'all don't want to miss class. But if you really feel like you need to go, like if you're in one of the classes that requires you to go, of course can do that. But I just want to let you know, in case you know of some people that really would love to see it, and it could be you too, okay? You can go if you need to. Lawson State is proud to present the Red Mountain Theater production. This is a semi-professional, production here. Lady Day at the Emerson's Bar and Grill. That's the name of the presentation. And that's this coming Wednesday, February 1st, 1 o'clock in the afternoon, right in the middle of this class, in the A.G. Gaston Auditorium on the Birmingham East Campus, okay? And here's the other thing they say, it's for mature audiences. Now, I know y'all are all mature, but the question is, it sounds like some of the language could get a little rough. And most of you probably heard plenty of rough language, but if you don't like listening to it, just let you know it's rated R. Okay. About the show. The time is 1959. The place is a seedy bar in Philadelphia. The audience is about to witness one of Billie Holiday's last performances, given 4 months before her death. I think she had sort of a tragic death. I believe she had substance abuse problems. I think that probably wrecked her health in many ways. And I don't know the full history of what happened, but I don't think it was very good, So more than a dozen musical numbers will be interlaced with salty, often humorous reminiscences to project a riveting portrait of the lady and her music. And she was an incredible singer. Unfortunately, got more notoriety in Europe than she did in the U.S. I think she was extraordinarily popular in France, for instance. But she did well in the U.S. too, but not nearly as popular as she was there. The cost, absolutely free to the public when it's on our campus, okay? Now, the college is paying for this, so you don't have to. So if you go to see it, at Red Mountain Theaters, they're going to charge you for it. If you go on our campus, they will not. And again, it's Wednesday the 1st, day after tomorrow, about 1 o'clock in the afternoon, A.G. Gaston Auditorium. That's on the Birmingham East Campus. Are y'all familiar with Birmingham East Campus? It's one across Wilson Road from Winona High School, okay? Not the campus where the administration building is, but across the road from that. The A.G. Gaston building is one of the larger buildings there. The nursing building is pretty tall, but A.G. Gaston is sort of spread out. The lead cast is Miss Yolanda London, I think in the role of Billie Holiday, and then Gabriel Elisha is starring as Jimmy Powers. I don't know. I'm guessing he must have been a manager or something, or maybe bar director. I don't know. But anyway, it is. But they do say again, rated R. So I'll leave that up to you. Okay, but since y'all are all in now, okay, everybody's heard. So let's see. Now, that's your sequence, series, partial series sub n. Let's say that we number, this is what the book does, n terms here. 1, 2, 3, 4, 5, 6, 7, 8, 9, up to n, wherever that ends. Well, the nth term would be plus 1 over the square root of n, right? Because the first term is 1 over the square root of 1, second term is 1 over the square root of 2, third term is 1 over the square root of 3, so the nth term would be 1 over the square root of n. All right. Now, that sum, that partial sum that goes to the n first terms, the first n terms of that. Now, that sum we know is greater than or equal to one over the square root of n plus 1 over the square root of n plus dot 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 plus 1 over the square root of n. Now, what in the world are they saying there? Okay. All right. Now, I don't think they're really clear on this. Yes. What? Oh, this is the end of 10.2 on page 529. It's example 9. Okay. Now, what do we mean by that? Now, they don't list, and I think what they're leaving out here is if they listed term by term, and I'm going to do it the way they did because I think they think this makes it clear, and maybe it did for them, but I don't think it does for me. But what if you listed for the first one here 1 over n square root of n plus 1 over the 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 square root of n plus dot 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 plus 1 over the square root of n. Okay? In other words, have n of these terms. The same number you had up here, only make these all 1 over the square root of n. Well, notice here. This is 1. This is about 0.7. This is something else. This is 0.5. 1 over the square root of 4 is 2. This is 1 over 2 is 0.5. So this would be probably 0.4 something, 0.3 something, and then whatever your n is, that's smaller than any of these before it, right? So you've got a bigger denominator, it's a smaller fraction. Okay. So if you had that, and that's saying that this sum is always greater than or equal to this. I don't even think it's going to be a possibility of being equal to. So I don't know why they put that in, but they did. Because this term you see is the same, but this is less than that. I mean, the n is greater than 5, so the 1 over the square root of n is less than 1 over the square root of 5. And this is less than that, this is less than that, this is less than that, this is less than that. For sure, without a doubt. In fact, all of these are less than the corresponding ones, except these and those are the same. So by all means, this top thing is greater than the bottom. Now they say greater than or equal to, but I think you could easily, legally say greater than. Okay, but what does this wind up being? This winds up being, how many terms do you have? N of those. So you have n over the square root of n, right? Do you? You have n terms, and they're 1 over, each term is 1 over the square root of n. So you have, this is your sum of those, right? Now, the question is that going to 0? As n's getting larger and larger and larger. Let's take some not so large number. 4 over the square root of 2. 4 over the square root of 4. What would that be? It would be 2, because 4 over 2 is 2. 9 over the square root of 9. 3. 16 over the square root of 16. 4, exactly. And you keep going. The larger you get, the bigger the number is. So this partial sum The more terms you go there, the bigger it is. This is a sequence of numbers, and that sequence of numbers is not going to zero. Okay? It can't be going to zero. So therefore, your S of n, if you do keep adding more things to it, it's getting bigger and bigger and bigger. Not converging to any number, because the partial sums are increasing, and they can't be increasing and get a convergence, period. Okay? So in other words, the actual value of that is the square root of n. So, I mean, whatever your n is, the 750th term, well, the partial sums of that would be the square root of 750. Okay? That's not converging to anything. That just keeps getting bigger and bigger and bigger. Okay? So, obviously, that doesn't converge. Because this thing, this shows that this term here, the partial sum here, is greater than or equal to this thing. This is greater than or equal to that thing. And this increases without bound. So that means it can't converge at all. Now, you could have used these same arguments. In fact, much easier if we had just done the 1 over n. That's the thing. That's getting smaller, but it's not getting smaller fast enough, because if you did the same kind of analysis with that, that'd just be 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus 1 over 5 plus 1 over n, and then did that as correspondingly 1 over n plus 1 over n plus 1 over n. Certainly, the denominator getting bigger, the fraction is getting smaller, so this thing would be less than that sum, not greater than, so it would be less than. And then you'd have n of those terms, and if you had n of those terms, that would be n over n of 1, and that is if that's greater, and your partial sum is greater than that, so yeah, it doesn't look like that could possibly converge either. But we won't go there. It's not as easy as I first thought it might be. So in other words, now here's a historical perspective. I think I told you about Archimedes trying to estimate the area of a circle. He didn't just stop at circles. This illustration here shows how he showed the area of a pyramid, showed that the area S of a parabolic segment is 3/4 t, where t is the area of the inscribed triangle, and then later he'll do other inscribed shapes. The more sides you have to those shapes, as you see in the book there, I don't think they have. Oh, sorry. Before we leave this other problem, here is a graph that illustrates what's going on here. All right. This is that we were just doing. The partial sums of the summation of n equal 1 to infinity of 1 over root n. The sequence, the terms, a sub n, which is 1 over root square root of n, those tend to 0, but they really don't tend to 0 very quickly. This is 1, 1/2, 1/3, 1/4, 1/5, 1/6, 1/7, 1/8, 1/10, 1/11, 1/12. They really don't go to 0 very fast. Okay? And if you add this series up, start with this one, then add that to it, and then add this to that, and that to that, you can see it's a curve that does like this. And don't expect, it may decrease its slope, but the slope never gets less than 1. And the slope's never less than 1. It can't be convergent. Well, let's see, it is less than 1, but it doesn't go to 0, I'll put it that way. It always stays positive, and the slope is always positive. It's not convergent. It can't be. For it to converge, you would have to have it would have to have a ceiling somewhere, and that doesn't. Okay. Now, let's see if they have. Yes, this is the Archimedes. I was hoping they had this on the slideshow. It was a figure in the book, but I was hoping it was. They actually did something with it. This is on the summary page. Page after summary starts. That will be 530 or so. Infinite series. Archimedes showed that the area S of the parabolic segment I don't think there's too much here that we ought to go into in great detail, because they don't really follow it up all that closely in the book. But this is an illustration of what we were talking about before. It's very similar to the circle being estimated by a circumscribed regular polygon inside and outside. And you let the number of sides increase, and you're getting closer and closer to the area of the circle, both from above and below. So he showed that the area S that's inside the parabola here of a parabolic segment is 4/3 T, where T is the area of the triangle ABC. Okay. Now, if you had, sorry, my throat's going. The best way to do that. You can calculate, and this is what Archimedes did, the exact value of the triangle. By the way, just to get a little idea of what's going on here. Notice that C and D are not necessarily in line. Okay? They have C being to the left of A. Okay? So, if you take that as sort of one part of the, well, that slope is going to what's going to truncate what we call parabolic segment. Okay? Now, these don't have to be vertical. Could be at an angle like that. If it is at an angle like that, then what they do is take the parallel line to that is tangent to that parabola. Okay? So you set up that and then connect these 3 points, C, B, and A. Okay, of course this line is the same line there. That then defines the area of the triangle inside. Okay. Now, this is how Archimedes did it. As we say down south, bless his heart. I mean, that he spent this much effort doing it. but he came up and proved this to be the case. He then did a triangle in here of what was left between this segment, and of course you would take the parallel to that and go here, and come up with another that would give you E. Do a line parallel to this one, D, that's tangent to the curve here, and that gives you here. So this is some area T. There's another area and another area, and keep taking the areas of each of those until you got so little area you couldn't figure anymore, or you got exhausted. This is sort of his method of exhaustion. And he found out that this area of the segment of the parabola was exactly 4/3 the area, always, okay, of that triangle ABC, where it's made up of this line CA and the point where B, where the parallel line to that crosses wherever it is. You might not be, certainly we work if C and A were lined up and this was right in the vertex, that would work too. But it works even if those aren't necessarily, that's not a right triangle, a right angle there. Now, so why did I go through all that? Archimedes did this in the 3rd century before Christ. I mean, before the Christian era. Way back there. I mean, close to 2,000 years before Newton and Galileo came along, and Gauss and all those other great mathematicians who did so much, and we're really awed by them. Archimedes did it 2,000 years before they did. I mean, some of these things, without the benefit of calculus, without a lot of the other things. So Archimedes could be a good paper topic. How he did this particular problem, that would be a good paper topic. So, just want to let you know there's some possibilities. Also in here is a reference to the harmonic series. That's another one that is a really decent paper topic that you could write on. So anything on Archimedes, anything on Galileo, Newton, Gauss, harmonic series, these, and just a couple pages before I thought, I don't see it now, I don't see it, but there's also mentioned here the mean value theorem. Basically, he was using way before it was proven 2,000 years later. Yeah, it's pretty incredible character. Oh, there's a couple more. Leibniz is mentioned here. Bernoulli brothers, Jacob and Johann. Leonard Euler. There's a ton of different paper topics just within that one little historical perspective. Guess what, though? This can't be your source. You have to go outside the book to find your source. All right, I can't remember. Did y'all like doing the preliminary questions or not? Up to you. Yes? Okay, let's do them. Let's see, are there any more slides here? No. All right, so let's do here. What role do partial sums play in defining the sum of an infinite series? What role do the partial sums play in defining the sum of an infinite series? Okay. Now, what would be your take on that? I harped a bit about this at the beginning of the section. When you're doing infinite sums, what are you summing? Basically, an infinite sequence. Okay, right? And we already talked in the last section how you determine whether the sequence converges, diverges, whatever it's doing. You know, and there are rules for that. Okay. So what does that have to do here? Well, an infinite sum is then taking those terms in an infinite series and adding them together. That's an infinite series. What's a partial sum? The partial sum is when you take so many of those first terms and add them together. That would be S sub n. And do all those terms plus one more, add them together. That's S sub n plus 1. So these partial sums make up a new sequence. And if that sequence converges to something, that's what the series converges to. So really, what do the partial sums, what role do they play in defining the sum of a partial series? Infinite series. I don't say infinite series. Okay? Well, they make up a sequence of numbers that you can then evaluate whether they converge or diverge. If they converge, then that's the sum of your infinite series. If they diverge, then your infinite series has no sum. Now, that's my take on it. Let's see what the book's description of it is. All right. 10.2. Preliminary question. The sum of an infinite series is defined as the limit of the sequence of partial sums. If the limit of that sequence does not exist, the series is said to diverge. So basically it's saying something like that. Okay. Maybe a little bit better words or clearer, I don't know. Here's number 2. Let's see if we can get it on here. That's number 1. Number 2. What is the sum of the following infinite series? 1/4 plus 1/8 plus 1 over 16 plus 1 over 32 plus 1 over 64 plus ... Okay. What is the sum of that infinite series? How can you determine that? What's that? Oh, it's going to 1? What made you think that?
Because the sequence is going to 0 very fast.
Okay. I agree that the sequence is going to 0. Is that enough to tell you the series converges? Not enough. Okay. Necessary, but maybe not, but not sufficient. Maybe in this case it is, but in general not. What is the sequence here? What is your... Say again? Okay. It's the summation of, you want n? Is that what you said? N equals something to infinity of 1 over 2 to the n. Is that it? I believe it is, isn't it? Okay. But this is n starting with 2. So it's a summation of n equal 2 to infinity of 1 over root 2. All right. Now, does that help us in any way? Is that indeed a geometric series? Okay. To be a geometric series, it must fit this pattern. N equal, I'm going to use the second one, M, this is on the top of 527, to infinity of C R to the N. Okay? Now, does that in any way resemble this? Well, 1 over 2 to the n is also 1 to the n over 2 to the n, all right? So that's actually 1/2 to the n, right? So this would be, wouldn't this, yeah, there we go. Wouldn't this be equivalent to that if C is equal to 1 and R is equal to 1/2? Wouldn't that work? Okay. Now, this formula that you have for that, this says that that thing right there is C R to the mth power, where our m here is 2, divided by 1 minus r. It's a geometric sequence, a series, that's what we showed by that formula, where C is 1 and R is 1/2. So this would be 1 times 1/2 squared divided by 1 minus 1/2, right? So this would be 1 over 4 divided by 1 over 2, which would be 1 over 4 times 2 over 1. I divided and then inverted and multiplied, and this would be 1/2. So that actually converges to 1/2, right? And I hope I pretty much know that's what it's got to say in the back. But let's get back there and see. And sure enough, 2s is equal to 1/2. All right. Now, I was going to do some more with it, but let's not. Okay. Yeah, I will do it. Just a little bit. Remember the figure on the previous page when you're adding 1/2 to 1/4 to 1/8 to 1/16? You know, that's that number line problem. Okay. If you start with 1/2 and add 1/4 to that, and then add 1/8 to that, and 1/16 to that, and 1/32 to that, and 1/64 to that. That's what we're doing right here, except that we're not starting at 1/2, you're starting at 1/4, which means you're not starting down here, you're starting 1 short of that. So you don't have this in the picture, so this is just 1/2, right? It's that same sum minus the 1/2. Now, I think you were going straight to the sum as if it started at 1. It's actually starting at 2. Okay. Probably more than you wanted to see on that. Okay. Whoops. Number 3. I think I'm going to need a clean page. So let's get it. What happens if you apply the formula for the sum of a geometric series to the following series? 1 plus 3 plus 3 squared plus 3 cubed plus 3 to the 4th plus ... And it goes on and on and on. What happens if you apply the formula for the sum of a geometric sequence to that series to that series? Well, that formula says that it's, by the way, looks like the C is going to be 1 and the R is going to be 3, right? Okay. And with that in mind, it says that series should add to C, which is 1 over 1 minus 3. So this would be 1 over a negative 2, which would be a negative 1/2. So that should add to negative 1/2. Do you think that's true? Could it ever possibly, in any stretch of the imagination, be true? No, it couldn't. Because 1 is greater than negative 1/2 to start with, and you're adding 3 to it, that gets you up to 4. Add 9 to that, add 27 to that. You're never going to get to be a negative 2. What went wrong here? The geometric formula doesn't work, does it? Yes, it does. But what's the requirement for the geometric series? Let C not be equal to 0. It wasn't. And if the absolute value of R is less than 1. That condition isn't met here. R is greater than 1. So no, don't even try it. It won't work because the requirement for the geometric series is that C be not, not equal to 0 and the absolute value of R less than 1. Not happen. Wrong condition. Your assumptions matter. Your givens matter. You know, if this, then that. If you don't have the if, you don't get the then. Right? Okay. Number 4. Let's start with a clean page here too. Is this making sense? Is it helpful? Help me think through issues. Okay, number 4. A student asserts that the summation, boy, you know if a student does it, it must be wrong. No, I'm sorry, I didn't say that, did I? Okay. The summation of n equal 1 to infinity of 1 over n squared is equal to 0. Okay? Because 1 over n squared tends to 0. The sequence tends to 0. So therefore, is the sum, is it equal to 0? And the question is this valid reasoning? No way in the world. Okay, because this is a sum, not a sequence. Okay? Now, I'll grant you the sum does converge, but it doesn't converge to 0. It can't possibly. What's the first term in the sum? 1. And then what are you adding to it? Positive numbers. Add positive numbers to 1, are you ever going to get down to 0? No way in the world. No, it's not valid reasoning. There's no theorem or anything else that would say that would be the case. So I don't know how much they wanted you to go in detail on the answer, but let's see what they give as their answer. Okay. Their answer is no. Okay. That's all. They didn't go into any more. It's just no. Okay. Number 5. Here comes that student again. Watch out. A student claims that the summation from n equal 1 to infinity of 1 over the square root of n converges because the limit as n goes to infinity of 1 over the square root of n is equal to 0. Is that valid reasoning? Why not? Okay. I couldn't understand all of what you said, but hopefully it included that's a necessary condition, but it's certainly not sufficient. Yeah, okay, that's pretty much what you said, right? But that's not enough, okay? You probably said more than that. We did it. Remember, we did that one just a little bit ago. And the limit to that we showed was the square root of n. And the square root of n has no limit. is a diverging. It increases without bound. So let's see. I don't know how much verbiage they want. I couldn't understand of everything that Emmanuel said, but let's see. Maybe he said exactly this. No. Okay. That's all it said. Is that valid reasoning? No. It was a student. What? No, I didn't say that. Okay. Number 6. Find an n. I think I'll go to a clean page. Is that okay? All right. Find an n. There it is. Okay. Such that S sub n is greater than 25 for the series the summation of n equal 1 to infinity of 2. Well, there's one surefire way we could do it. Yeah, add them up, exactly. And that would be 2 plus 2 plus 2. That's what it's saying. The summation of 2 on to infinity. Now we want some partial sum that's going to be greater than 25. We want to find an n that guarantees that to be true. Well, what does that sum add to? This is the whole summation S series. We're looking for S sub n. And S sub n is simply going to be, that's letting the first n terms, that's going to be 2n, isn't it? Or 2 capital N. Right? Because the first sum is going to be 2, the second term is going to be 4, the third term is going to be 6, the second, sum. First sum is 2, second sum is 4, so third sum is 6, fourth sum is 8. So basically your nth partial sum is 2 times that capital N, right? And you want that to be greater than 25. Right? Because S sub n need to be greater than 25. So what n would it be? Divide both sides of that by 2. You got n greater than what? Second? 13. I would say 13. Now let's see how they define n. If they define capital N, which I think they have to, as an integer or a counting number, let's say, then you could actually say 12. If you don't let n be 12.3, if that's the case, it's not going to work. But if n and the partial sum, that's after n terms, it's got to be a counting number. So actually any n greater than 12 would be 2. 13 would be greater than 12. So I think they can allow 12. I would. Let's see if they do. No, they said n equals 13. Okay. Yeah. But I think since n is a counting number, you could even say n is equal to 12. Certainly n greater than 13 is going to work too. Okay. And all they said was find an n. They didn't say find the least n. So I agree with you. 13 certainly works. All right. Let's do the 7th. This has more preliminary questions, I think, than any section I've done so far. Number 7. Does there exist an n such that S sub n is greater than 25 for the series summation n equal 1 to infinity of 2 to the minus n? Does there exist a value n such that the partial sum for that value n is greater than 25 for this summation. 2 to the minus n. Just because they're so convenient to work with, I think I would rewrite this as a summation n equal 1 to infinity of 1 over 2 to the n. That's the same thing, right? Which would be a geometric sum with c equal 1 and r equal 1/2, right? Now, our formula for that, and this is with n equal 1, remember what that was? The s of n, but s is equal to 1 over 1 minus r. Wasn't that it? From the top of page 527, c over 1 minus r. And our c is 1, our r is 2, so this would be 1 over, r is 1/2, so 1 minus 1/2 would be 1 over 1/2, which would be 2. The sum of all that is going to be 2. Can you get a partial sum that's going to be greater than 25? No way. All right. Because you're adding positive numbers to it, and there's no way you can get that to add up to have a partial sum of 25, and you're adding positive numbers to it and ultimately get the 2. Just not going to happen. Okay? So that looks pretty definitely like a no. How do they answer? No, S of n is increasing and converging to 1. How did I get 2? Oh, maybe I did in it. Let me check one thing. I wasn't paying close attention. Nah, that's how it was. This is true for n equals 0. N equal 1, you'd also have the term in there. I used the wrong formula. Okay. It's CR to the m. So that would be C, which is 1, but then you have a R to the nth power, m is 1. Okay, so that would be 1/2 over 1/2, which is 1, not 2. Okay, I was doing from C equals 0. This is from C. N equals 0. This is N equals 1. Okay. So, where are we here? No, S of n is increased, it converges to 1, not to 2, but to 1. The formula is not valid because a geometric series with, wait, I'm looking at the wrong thing. Converges to 1, so S of n would have to be less than 1 for all n because all of the terms are increased. So they say pretty much the same thing we did, except they use the wrong number. Okay, but still, 2 or 1, it's not going to get the 25. Okay. Now, the last one here. Give an example of a divergent infinite series whose general term tends to 0. I think we've done several of those, haven't we? Give an example of a divergent infinite series whose general term tends to 0. Say again? Summation n equals 0 to infinity of, we've done at least 2 of them, and you could do infinitely many more. How about just 1 over n? Yes, sir. Howdy. Oh, I didn't check. Yeah, I did check to see if the door was unlocked. Sorry about that. Okay. we've already, I think, shown that doesn't converge, is the diverging, but 1 over n certainly converges to 0. 1 over n, 1 over 2, 3, 4, 5, 6 is going to 0, but the sum does not. And let's see which one they chose. Square root of n, 1 over square root of n works too. Let's see, because we did that at least twice. Oh boy, they put a real good one in here. Here's the one they chose. The summation, they chose from n equal 1. It doesn't matter where you start it. Of 1 over n to the 9/10. Okay. Why they chose that, I don't know, but it certainly works. In fact, anytime this exponent is 1 or less, this is not going to converge. If it's greater than 1, yeah, it will. So n to the 10/9 would have converged. 1 over n to the 10/9. 1 over 9/10. That one doesn't either, and that one's actually less. Okay. That took long enough, didn't it? Okay, homework exercises in 10.2. Any of the let's see. Do number 1, it has 4 parts. Do either 3 or 5, or both if you choose. Do 7. Do 9 if you have a computer algebra system, or get started on it, think your way through it. If it gets too bogged down mathematically, you don't need to do lots of calculations. But try 11, any of the odds 11 through 15. Do any of the odds 17 to 21, and any of the odds 23 to 35. Do either 37 or 39. I think we did something like that in class. Do 41. Well, let's see. I'd say any of the odds 41 through 59. I'll let you choose which of those to do. You might want to do more than one, but do that. Further insights and challenges. Just glancing through here, I see a Gregory-Leibniz formula, okay, and I think we all know who Leibniz was, and if no one's written a paper on him, you could do him, but who in the world was this Gregory dude? You might want to do a paper on him, or how did the two of them, either together or separately, come up with that formula? What difference does the formula make? I mean, there's several paper topics you could have on that one. There's another, 64, refers to Cantor's disappearing table. So who was Cantor? You know, you could write about him, or where does this problem originate? How did he do it? What was the purpose of it? Blah, blah. Then, the next one, number 65, is referring to a Koch, I think is how you describe it, snowflake, by Swedish mathematician Helga von Koch. And they show sort of an example of that, and I'll let you decide whether you want to write on who she was and how she came up with this problem or whatever. Okay. Now that's all we're going to do in chapter 10. If we had more time, we would definitely do some more of this, but I just want to point out to you some other things you can look at. Harmonic series, that would be a potential paper topic. An important thing in physics. There's a little blurb on the, I don't see anything that would be all that useful. I was thinking there might be a paper topic there. You might find one, but top of page 537 in the margin. And you have a few other issues there. 10.4 is absolute and conditional convergence. Sorry, we don't have time to do that. It's can be a little tedious, but it's not really all that bad. 10.5 is really neat stuff, the ratio and root test for strategies in choosing tests. If you really find this stuff interesting, you might want to look a little bit at that. By the way, I just happened to, when my eyes fell on it, reading that, on page 548, the end of the problem set for 10.4, which you don't need to do, but it mentions the jeune, I think it's how you pronounce it, Dericlay, and he's a potential paper topic, and he's referring to the great French mathematician Augustin Louis Cauchy, which I think we've mentioned before. So anyway, there's two potential paper topics there, and that gets to one of the limit comparison tests. So that is the stuff that interests you. You could write on either of them or that. Then ratio and root tests, strategies for choosing tests. It's a pretty good summary of the various things you can try, if infinite series are your things. Then the power series is mentioned in the next section. Too bad we don't have time to do that, but we have hinted at some of the portions of that, and I'll let you decide whether you want to look at it anymore. Not going to be tested over it, but if you're just interested in it. And somewhere, this is a huge chapter. 10.7, I wanted you to at least hear this. I'm not going to go over anything. If this had been during your Cal 2 course, I would have at least done a slideshow on this. We don't have time for it now. Taylor series, one of the most powerful of all your infinite series, and basically every time you use your calculator, it's doing a Taylor series for you, okay? And it's testing it and giving you an answer. So not a bad idea to look at that. One of the most famous, and then right under Theorem 1, you'll see the Maclaurin series. That's a special subset of the Taylor series, okay? So you can write on either, and this Taylor guy, he has a strange first name. It's almost sounds like a female name. Right now I cannot remember what it is. But then Maclaurin, he was a good Scottish guy, and you can proceed there. Again, this is a fairly long section. Some of my pages are stuck together. Binomial series is mentioned here, which has buku applications. Elliptic integral mentioned. Okay. But again, you don't have to do that, but it's well worth a review. Missing anything here? All right. That done, let's move on to, let's see, before I do that. Yeah, I can't go back. Okay. I think we were through with that. Yeah, that was the last slide. Okay. So we end that. This is where I started the day, thinking we were going to start in chapter 11. Then I realized, we didn't quite finish 10, too. So let's go to 11. And I think I told you, let's see. Yeah. I think we're just going to do 2 sections here, and then I'll give you your first test. Isn't that what I told you before? Yeah, because we won't do polar coordinates. If you need them, they're there. You got the book, use it. Okay. Goodness, my throat's hurting. All right, pretty picture here. Yeah. Blow it up. This is from the old text. This is in yours. It's not in the new text. There's something else as your lead-off picture, which is pretty important, but I don't think it's pretty. Okay. I can't get my cursor to locate. Get there. It's driving me nuts. There it is. Finally got it. Okay. Okay. This is a beautiful shell of a chambered nautilus, rose in the shape of an equiangular spiral, a curve described by polar coordinates. So this is going to be talking about stuff we're not going to get to. R is equal to E to the A theta. And it seems like I mentioned in here, it may have been in one of my other classes. Have any of you ever heard of the golden ratio or the Fibonacci series? Yeah, we talked about Fibonacci series. These things are put together according to those same ratios. It's amazing how many things in math and in science and natural science all fall back to some of the same concepts over and over again. Now, I can't remember if I said it in this class. I know I've got my first paper in this class. Way to go. But the rest of you, please get yours in too. There is a book. I used to have it on reserve. I think they put it back on the shelves. It's called, in very simple title, The Math Book. Okay. And I can't think of the author's name. It's sort of an unusual name. Right now it's flying the coop. But it's actually, see, we have some German friends, and just about every one of my birthdays for several years now, they've given me a book, which I love books, okay? And they must have figured that out, and that's what they've given me. And several years ago, they gave me this book, and I read through it. It's 250 of the most important discoveries in mathematics, okay? And every page has that discovery on this side and some illustration or picture or something on the other side, beautifully done. Something like this or something even better that they show, and that illustrates what they were just talking about before. And that golden ratio, Fibonacci series and stuff like that, it shows up. I'm trying to recall now. It's been several years since I read it. I'm guessing something like 5 to 9 times, something related to that does. And by the way, there's 250 potential paper topics right there. I mean, don't use the article, but look, they're beautiful to look at, fascinating to read about. Now, I'm not saying all 250 all that fascinating, but some of them are just incredibly amazing in things they're showing. So anyway, too much on the picture. Let's get started. Parametric equations. This chapter introduces 2 important new tools. Okay, first we consider parametric equations, which describe curves in the form of particularly useful for analyzing motion and is indispensable in fields such as computer graphics, computer-aided design, then polar coordinates. Now, we're only going to do the first of those 2. If you're interested or need the others, then by all means look at them. Chapter closes with a discussion of conic sections. Wish we had time for it, but we really don't. So if that's of interest to you, that's the last part. So we'll start with 10.1 and parametric equations. Imagine a particle moving along a curve. Okay? How are we doing on time? Are we out of it? Yuck. Almost. We have about less than a minute. So what we have is a particle moving on a curve. Now, it's not bad, except if you notice that curve I just randomly, I did it on purpose, that curve is not a what? a function, because the curve itself, there's more than one y for any given x. But that curve still could be a curve in nature. So how we describe that is describing the curve in the parametric form. Don't have x being the independent variable. Have something more basic like t is the independent variable, and then for any given t, your x can repeat itself, because the t's don't repeat themselves, but the x's could. That's okay. And then have y as a function of that same variable t, not of x, but of t, and then what we have is a parametric equation. And that's where we'll start next time. I think we are probably out of time now. So we'll begin there next time. Okay, we didn't get much done, but we talked about the picture, and we'll start with this right here. Okay, good deal.